What's up, physics people? Let's talk some electricity today. So hopefully you got a little bit of a start on it yesterday. We'll talk about the lab a little bit as we're going through stuff. So if you've got the questions to the back page, we'll kind of hit a few of those as we're going. So I would have that out, and then you can add to that as you want. The notes are online. We're only going to get through part of the set of notes today, but the whole set is there under Wednesday. So let's just go ahead and go through stuff. Make sure we've got a good handle on things. So current electricity is flow, right? There's static electricity, which is when you build up a set of charge and then it gets a place to discharge and boom, all at once. Current electricity is flow. I think a great way to think about those two things is water balloons versus a fire hose. We can do things like the little Tesla coil and the Van de Graaff generator with pretty high voltages without causing damage because they're like water balloons. Those are static electricity. It's a one shot, a bunch of electrons hit, they might smack, but they don't do damage because they don't continue to go. It takes current to actually really do damage, right? So current electricity is flow of electricity. There's alternating current and direct current. We're not going to worry about that a whole lot today, but those have historically been really, really important, the difference on those. For those of you that don't know, alternating current is basically what everything in your house is. Some things a lot of things that you use have to change that into direct current, but direct current has a lot more resistance. So it's not used to transmit large amounts of electricity long distances. But some things like a computer don't work well on alternating current. So you have to have a transformer, not Optimus Prime, an actual physics transformer, to transform that from current or from AC current to DC current, right? Direct flow current. But we'll get into that stuff more later. Electrons are moving in a definite direction continuously through the conductor. The conductor does have some resistance as you go through it, so that electricity will drop over time. Electrons are going to flow from where there's a lot of electrons to not very many electrons. And the force of those is referred to as the electromagnetic force, the EMF. Those of you that are in AP chemistry or were in AP chemistry might recognize that EMF when we were doing galvanic cells and stuff. We'd call that EMF the electromotive force on our galvanic cells and that kind of stuff. But that the separation of charges, that electromotive force, that's another way of saying voltage, basically, right? So the EMF, referred to as the potential difference that exists across a battery or generator. So when we just hook up a battery to a voltmeter and see if it works or whatever, that is getting our voltage. We'll do a few of those things here in a few minutes. I'll switch to a different view so you can see that, and I'll set a couple of those things up, and we'll measure that. But that potential difference is another way of saying voltage, right? Voltage is how we measure the potential difference. When we draw our circuits, this is how we typically want to draw them, something like this, right? So you draw the source of electrons is usually a dry cell. It's usually a battery. There is a short little vertical line and then a longer vertical line. If you have multiple batteries together, you'd go short line, tall line, short line, tall line, short line, tall line kind of thing, right? That'd be like 3 batteries. Each short line, tall line set is 1 battery, right? So, but I can look at multiple batteries in a row, and that's just fine, right? You draw the wire. We typically draw it in straight lines. They do not lay in straight lines when they're on the tabletop, but students will sometimes draw so we want it to be easy to read. So draw it like it's square, right? This is about as rounded as you ever see something in circuit diagrams. Then there are lots of different drawings for what the load is. If it's a light bulb, it looks like one thing. If it's a fuse, if it's a speaker, those all have different drawings, and we'll kind of get into those as we're going. Then you have a switch. This switch is showing that it's open. Because you see how it's not connected? If this switch was straight across, then it would be connected. So this is an open circuit. Do the electrons have a path, right? So if I can go all the way around in a circle, the electrons have a path. So I'm going through here, and the electrons don't have a path. So this is an open circuit. No electrons will be flowing in the circuit. The electrons have to be able to go all the way around in order to do that, right? That is part of Kirchhoff's loop rule. I bet no one could guess what nationality Kirchhoff is. Kirchhoff is, that's right, Hawaiian. No, he's not Hawaiian. He's Russian, right? That's a Russian name, right? So Kirchhoff's loop rules, there's a bunch of them. We're going to just touch on them a little bit. But one of the things you can do with that is if you can't go all the way around in a circuit, it's not a closed circuit. Electricity won't flow in that circuit, right? So that's a couple of the basic things there. Some things in our houses, right? Electric plugs. The stuff's gonna leave the negative end of the terminal. The wider part of the plug. Have you ever noticed that on a lot of, not all, some things it doesn't matter. They can go either direction. But a lot of things have a wider prong that goes in the electrical outlet and a narrower prong. The wider one is the negative prong and the narrow one is the positive prong. So those, it matters what directions the electrons coming through there, right? So, but the electrical in your house, it's alternating current, but we're gonna pretend it's not for a second. It's gonna come out of the electrical plug, go do a job of some sort. When it does that job, it uses up its voltage, and then it comes back. So you have to regulate how much electricity is going to go through there. If you do something stupid, like I shouldn't use the stupid. My daughter grumps at me when I say stupid because that's too mean. If you do something ill-advised, like plugging something in without a job to do, like a paper clip in an outlet, like I know somebody, I believe in your class, yeah, that was your class, not your physics class, like your graduating class, did. There's no work to be done. First law of thermodynamics is that all energy has to be either work or heat. So if you don't give it any work, then poof, it all turns into heat and it blows up and pops the circuit breaker. And there's no resistance. If the resistance drops, the current goes really high, right? All kinds of problems, right? Loads is the things that you're doing. That's the fan. That's the TV. That's the computer. That's the explosion of the, well, no, that's not a load. There wasn't a load there. That's why it's a problem, right? And switches control the circuit, right? The light switch in your house is literally just a switch. You break one of those apart and look inside it. It's literally just a piece of metal that's either connected or not connected, right? It's pretty straightforward. Fuses and circuit breakers do the same job. A fuse or a circuit breaker, a fuse is something that is a one-time use thing that basically has a piece of metal inside it that if too many electrons pass through it, generates too much heat and it melts the thing. It melts and cuts the flow of electricity. A circuit breaker does the same thing, but basically it just flips when there's too much electricity that goes through it. It pops and opens and is basically a switch then, and it's a switch that broke, and so you have to go down and repop it the other direction. If that happens over and over and over and over again, you can break the circuit breaker, but circuit breakers in general can be used more than one time. Something to keep in mind, in general, house fuses will blow at 15 to 20 amps. There are some things that use close to that. So if you use multiples of those, then you'll blow circuits and stuff like that. We'll kind of get to household things more later on, but I do like to hit a few of those common household things here at the beginning. So yesterday, kind of what you got into was the Ohm's law stuff. So this is Ohm's law. There are three parts to Ohm's law. There is resistance, which is opposition to the flow of charges. Again, using the water example, that's like the things in the river slowing you down, right? So that's the opposition to flow of charges. Wire has that, but it's not very much. So if you hook up just wire, there's not a lot of resistance, but a wire does have a resistance. So a long wire will have some resistance. First law of thermodynamics, if there's a lot of resistance and stuff, that will generate some heat. My dad made a mistake one time of I like to make fun of my dad. He hooked together something small. I don't remember what it was, but something in a garage that was continually using electricity. I don't know if it was a heater or what it was. No, it wasn't a heater. It was something that used just a tiny bit of electricity, but I think it was a fan. Yeah, it was a fan because he was doing some staining in his garage. And he took like a 200-foot electrical cord and he had it all wound up in a circle. And then it was hooked up to a small fan. And the fan wasn't pulling much current, but because it was such a long, like 200-foot extension cord that was all wrapped up in a circle, the extension cord had a little bit of resistance in it. And so it was generating a bunch of waste heat. And it ended up melting the extension cord and caused a short where, that's basically what the paper clip in there, that's a short. So there's no job to do there. And it blew a circuit breaker and the fan turned off and he ruined a 200. It was fun. Anyway, so the higher the resistance, right? If we look at resistance, the higher the resistance, the lower the current, right? So if you're looking at number 9, what effect does doubling the resistance have on the current? Doubling the resistance would cut the current in half is what you should have come up with yesterday. So if you're looking at your answers from yesterday, which you should, right? If I double the resistance, that cuts the current in half, right? Because the voltage stays the same. Another way, I guess you could look at that is right here, right? If I double R right here, that's going to cut my current in half. Voltage is, this is current. voltage is a potential difference, the push behind the electricity. The higher the voltage, the higher the current, right? So at a given resistance, so resistance drops out when that's straightforward. I raise my current, my voltage, I raise my current. We'll look at that here in a couple minutes. I'll set up a couple little circuits and we'll look at that. And then again for current, the higher the voltage, the higher the current, the higher the resistance, the lower the current, right? So that's how those three things are related. I think that's a pretty like straightforward relationship kind of thing. That's why National Lampoons is kind of a problem, right? Because he hooks up all of those different light bulbs to one electrical outlet. So it's going to be a whole bunch of resistance. So that you would need too much current to make that work. And so the house would continue to try and give you more current because it's not a set amount of voltage. So it would increase the voltage trying to get enough current through there. And it would blow the circuit breakers and all that kind of stuff, right? That's why you can only hook so many light bulbs up in a row. The new LEDs have a lot lower resistance, so it takes a lot less current to get them to light up and stuff, right? So they can keep a pretty low voltage. We look at the labels, right? There's that omega symbol, that like horseshoe looking thing. There's the amps and there's the volts. When we look at some ideas here, right? A thicker wire is going to use less resistance. A longer wire is going to use more resistance. A thin wire is going to use more resistance. A short wire is going to use less resistance. So when we measure things in lab, if the idea is it should be 3 amps or something like that. Well, it'd never be 3 amps. That's too much. But 0.3 amps, you'll actually end up getting like 0.25 amps or something because there's a little bit that gets lost in the wires, right? So anyway, the current, the greater the resistance, the less the current, the greater resistance, and then the more batteries, the more powerful the batteries, the greater potential difference, right? So we'll couple examples real quick and call it a day. Oh, hang on. There were a couple other ones there. What effect does tripling resistance have on the current? That would cut it in 1/3. And then down here for number 12, if your voltage is 24 volts and your resistance is 10 ohms, that's going to be a 2.4 current. If the voltage is 12 and the resistance is 40, that's going to be 12 over 40. 12 over 40, well, 12 divided by 4 is 3, so that's going to be 0.3. And then if you have a voltage, right, so the second one there, 12 volts and 40 ohms, that should be 0.3 amps. And then for the last one there where you've got 6 volts and 4 amps, the resistance there, if we're going, let's see, in my head there, voltage, current, and voltage, right? So current and voltage, this is always the weird one. Yeah, so you take your voltage divided by your current, so your resistance must be 1.5 there. Yeah, 1.5 ohms for your last one. Okay, now we'll actually stop and go jump and look at a couple examples.